Okay. So guys, today we're going to be looking at the student exploration golf range assignment. So when you click on that, it's going to open up to this Google Doc. So to get to the website, you click right here on this blue student exploration golf range. If you click on that, okay, it's going to have the link there embedded for you. So we open that guy up. And then from there, we're going to launch our gizmo. All right, so we have a bunch of different things that we can change. We can show paths, we can show grid, we can change our degree of launch, we can change our initial velocity of our launch. And we can then also change our atmosphere from air to none or no atmosphere, which would basically be like a vacuum. So first thing is we're going to talk about a couple of these terms today. Acceleration, air resistance, gravity, hang time, launch angle, projectile motion, trajectory, vector, and velocity. We should have seen 1, 2, 3, 4. Talked about air resistance on Thursday, Friday. Launch angles should be relatively straightforward. The angle at which we're launching it from the ground, right, from the horizontal. Hang time is essentially just the total time the object is in air. So the one that and trajectory hopefully is, you guys are somewhat familiar with that term, just being from years of math that you've done. It's going to be like the path that the object takes through the air. And then so projectile motion is going to be like our biggest new thing. So before you answer these guys here, or before we get to the meat of this, you're going to answer these 2 questions to the best of your ability. You're going to contest with your friends to see who can drive a golf ball the farthest. So would you want to hit more of a line drive, a ball that's relatively lower to the ground, or a shot with a very high angle? And explain. So after you guys have answered number 1, think about number 2. Golf balls will be able to drive much farther than major league home runs. Why might this be? So again, based off of your knowledge, which of the 2 is lighter? Probably the golf ball. Okay, well, does it mean then like the lighter the object, the farther it's going to go? That may have something to do with it. But wait a minute. When we did our lab last week, when we did the simulation with our with free fall, we did the free fall simulation. We wound up figuring and getting that, right? If we went to the free fall lab. Okay, if we drop that, say, the shuttlecock versus something that's even lighter, the cotton ball. So the mass, right, the lighter object, which is the lighter object of those 2? Cotton ball. But it traveled slower. All right, well that doesn't make sense. Figuring what we were trying to talk about, right? We said the golf ball is lighter than the baseball, so maybe that might have something to do with it. But what does that actually mean? That meant that if we're saying that the lighter it is, but the lighter object here, the cotton ball, moved a lot slower than the shuttlecock did. So does mass come into play with this? Maybe. But let's think more in terms of what else. What were the two things that we said from this lab here that would affect our speed? Well, the height has something to do with it.
Air resistance.
The air resistance. So what two things kind of really dealt with or affected the air resistance? It had to deal with the mass of the object, and it had to deal with the surface area, right? The area that it was taking up. So that's why, like, the cotton ball has relatively the same surface area as the shuttlecock, but its mass is lighter, so it's going to be affected more by air resistance. So let's just say, for this example, the baseball and golf ball had the same mass. Which would be more affected by air resistance? The golf ball or the baseball? It should be the baseball, yeah, because it is larger, essentially, like, more air is going to wind up like hitting it, causing it to slow down a little bit faster than the golf ball would. All right. Not to mention that you can also get a greater initial velocity from a golf ball than you can with the baseball. So that has definitely a factor as well. But you would probably want to venture to say that the air resistance is going to wind up affecting the baseball greater than the golf ball. Something along those lines. Okay. So from there, have you ever hit a hole-in-one? You're going to have a chance to do that in this golf range gizmo. You're going to see how a variety of different factors are going to affect the path of a golf ball. The movement of objects, such as a ball, through space is called projectile motion. So projectile motion, all right, is going to wind up moving through the air or moving through a vacuum under the influence of gravity, and we are going to wind up seeing the effects of this. So first thing we do is we're going to press play. Did the golf ball go too far, the right distance, or not far enough? So let me get out of that. Let me go back to boo. So yeah, did it go in the hole? Did it go too far? Did it go too short? It fell too short. Fell too short, or not far enough. Now it says click the reset button and move the initial velocity sliders and the angle sliders. So we can adjust the velocity and launch angle until you get a hole-in-one. So what you guys are going to do is you're going to wind up changing the velocity and or angle in order to get yourself a hole-in-one. And whatever value you wind up getting, you're going to write down. So let's just say this hit. I don't think it will, but just a little short. Oh, dang. So maybe I'll then just try and change this just a tad. Too far. What? Are you kidding me? That's just ridiculous.
Hole-in-one.
Hey. So you guys go, there's multiple combinations of initial velocities and angles that you can wind up hitting. So you're going to go through, you're going to go and you're going to type in what you had for initial velocity and then what you had for launch angle. And then for the third one, it asks, can you get holes in one using other combinations of initial velocity and angle, launch angles? Yes, you can. If so, give an example. So try and give 3 examples. So your first hole-in-one, you're going to write initial velocity and angle here. And then I want you to do 3 more examples of velocity and angles that you got to get a hole in one. All right, so you guys, I'm going to give you guys 4 or 5 minutes to do that real quick. So after you guys have gotten your first velocity and your 3 examples, we're going to move on now to activity A. All right, so we're going to get the gizmo ready. We're going to try and right now achieve maximum distance. So we're going to click the reset button. We're going to make sure that the atmosphere is air. We're going to set initial velocity to 75 and the angle to 45 degrees. All right, so atmosphere is air, bam, 75 and 45. And then what does it say to do? All right, question. Which launch angle do you think will produce the longest drive? So before we fully begin here, if I took out the air resistance, there is going to be a piece of information. So any 2 angles, right, like any 2 numbers that add up to 90, they're going to wind up landing at the same distance if we neglect air resistance. So if we take out air resistance and we're just doing it in a vacuum, JC, pick a number. 23? It's close enough. Damn it. Damn it. Damn it. Okay. Now I'm going to just put show path. Holy crap. I'm going to clear paths. Redo that real quick. Okay. So it lands this distance. What plus 23 is going to give me 90? 67. Think so. So this should land in the same spot. But because we have a larger angle, it's going to get more height to it. And oh snap. All right, let's think of another one. 30 degrees and so we got 30 degrees. Okay, what is 30 plus or 30 minus 90? 60. So it may not have gotten as high as the 67 degree guy, but it did go a little bit farther. Okay, so it seems like the farther we got away from 0, the farther this object went. And then or the farther we got away from 90, the farther this went. So let's try 40. Let's try 40 degrees. Yahtzee. Okay. And then 90 minus 40 is going to give me 50. So this should land right where the yellow hit. Okay. So the farther we got away from 0, the farther the object went, and the farther we got from 90, the farther they went. What is the 1 degree that is equally distant from 0 and 90? It's basically just 90 divided by 2. Going to give us 45. So this is going to give us the best combination of vertical velocity and horizontal velocity. Now it's difficult to see, but it is a little bit farther than our other guys here. So 45 degrees is the premium launch angle, neglecting air resistance. All right, so we're going to just keep that in mind as we go here. So what launch angle do we think is going to give us the longest drive? Probably 45 degrees, or very close to it. All right, but we're supposed to make sure that we have air on. All right, that may change some things up. All right, so we make sure that the air is on, 75 and 45. Turn on show grid box. All right, show paths and experiment with a variety of angles until you find the one that gave us the longest distance. All right, so I'm assuming that it's going to be right around 45. Now let's see if I just kind of increase it like to 50 by 5 degrees. Let's see if that worked. It's going to have a little bit more height. Okay, it was shorter. It's kind of what we thought. Well, what if we made it a little bit less than 45? What if we made it around like 40 degrees? Should this technically go farther or shorter or longer? Well, I just farther, same distance, shorter than the 45-degree guy. You think what? Well, didn't we just do in our examples that we did the with no air, like 50 plus what equaled 90, right? So the 50 landed here where this teal shot was. So based off of what we just did without the atmosphere, without air, all right, it should land in the same spot as the teal. But it went a little bit further. It went a little bit farther than our other guy. Okay, we can't. I haven't figured out the way to do this yet. To zoom in, nice and in on it or one particular spot. So let me just see. Can I do this? This is probably the best thing I can go for. So that was the green shot. It looks, dang, that's very, very close to that 45. Make it like 42. Maybe that would be a little bit better. That's, dang, that's super close as well. All right. So if you can't decide on one specific value, you can give a short range. So maybe somewhere between 40 and 45, they seem to give us the best range. They seem to give us the farthest range. So that would be something maybe you would like to think of or use for number 2. All right, then how far did the ball travel? Kind of got to zoom in here and break down what each of these lines represent. So this is 350, this is 400, and each of these little grid boxes, we got 1, 2, 3, 4, 5, so that would be probably what, 360, 70, 80, 90, 400. So these objects landed in between 370, I'm sorry, 360 and 370. So I'm probably going to say, like, yeah, they're probably closer to the 370 mark there. You guys agree? Yeah. Okay. And then it said to like, okay, click reset and turn on show paths, clear paths, take a swing at the premium launch angle. Does the curved path of the ball appear to be perfectly symmetrical? So I'm not even going to bother with that because we have a couple little examples here. Do these lines look perfectly symmetrical? You know what? Let's just take that guy off. Let's just shoot another one. Does that appear to you guys to be perfectly symmetrical? No. Which side's a little funky? The right side. Well, I guess technically either way you look at it, but based off of the original launch, this seems to be, the right side seems to be a little off. So does it appear to be symmetrical? Not perfectly, no. Not perfectly. Does anybody know what kind of shape this is, by the way? Technically, use it in math class, probably when we were graphing. What would we call that kind of shape? Begins with a P. Parabola.
Parabola.
There you go. So projectile motion, the path that these objects are going to take, all right, whether it's a ball or a box, a shoe, I don't know, something, baseball, something that you can launch through the air, a little rocket. For the most part, they're going to follow some sort of parabolic path. Now, the shape of them can change depending upon their components of x and y. So if we give it more y, it's going to go a lot higher than, all right, let's see, this should be right about the same. Oh, dang. So even though it has the same initial velocity, you're going to make contact with the golf club at this speed, the angle at which you hit it, though, is going to greatly affect the characteristics of it, whether it is a high arching shot or a low line drive kind of tee shot or just regular shot in general. So the curve would be slightly steeper over here. It's not as elongated on the right-hand side, and that is due to the fact that we have some air resistance going on. So then if we clicked reset and then we turn, let's clear some paths, let's turn atmosphere off. All right, which launch angle produced the greatest drive? So again, if the two angles add up to 90 degrees, they should land at the same distance when we have no air resistance. So I don't know, 15, if we did 15 and we did, what would the other one be? 15 from 90, 75? Did I? Oh, yeah, there we go. Same base. Okay, well, what do we, again, what is the halfway point between 0 and 90 is 45, and that's going to wind up giving us our greatest distance here, or very, very close to that. I mean, it's difficult to zoom in, so we can't quite get as accurate a reading as I'd like. Or maybe we can zoom in, but I can't fully quite tell. This one's a little bit shorter. This one should be a little bit higher, but still relatively short. Still going to wind up falling short of this guy. All right, so 45 degrees, or very close to, is going to give us the longest drive. How far did this thing travel? Oh, crap. Zoomed out too quick. So let's go 45 or 50. Oh, wait. Why don't I do 50? I don't want 50. I want 45 is the farthest. Five. Ooh, dang, that's far. What is that at? That is at, if this is 550, 560, 570, 580, 590, 600. It's in between 570 and 580. So you could just give that range, 570-580 meters. All right. And then it asks, why do you think the ball traveled farther in this situation? Hopefully it's pretty obvious. We didn't change anything but what? It was the only part of the experiment we changed as far as our launch angle here. Well, we didn't. If we said, okay, 45 gave us the greatest distance, we kind of decided maybe 45. Okay, We didn't change the initial velocity, and we didn't change the angle. What did we change? Yeah, we wound up changing whether or not we are launching it in a vacuum with no air resistance or in an atmosphere where we do have air resistance. So here's the same shot, same initial velocity, same angle of launch. And look at that difference. All right, this is at 370 to 380-ish, and this one's at 570 to 580. So a big difference, even though you're hitting it with the same exact initial velocity and you're hitting it at the same launch angle. All right, so air resistance can play a very, very big factor. And then number 5, it asks you to extend your thinking. The moon has less gravity than Earth, and it has an extremely thin atmosphere. So basically, essentially a no atmosphere. How would those factors affect the trajectory of a golf ball on the moon? Okay, so this light pink guy here, that was air resistance. This purple or whatever, I don't know what color this is, that is on Earth with no air resistance. All right, so then let's say moon, little to no atmosphere. Crap. What is the moon's gravity? It's about 1/6 of Earth. So let's see. 9.8 divided by 6. We're looking at around 1.6 and change. So we're going to go to advanced features, and we're going to change the gravity to about 1.6. Okay. Now, if the moon, actually, you know what, let's say the moon had an atmosphere. All right, we can't really change how thick it is, but let's just see what it would do on the moon if it had the same atmosphere as Earth. Wow, it's taking a lot longer. Ooh, that shows a really nice how the air resistance really affected that shape. It should be like perfect parabola if there is no air resistance, but you can really kind of see it here. This side gets bunched up a lot more. It's definitely steeper on this end. All right, well then let's take out the atmosphere. Well, shit. Shit. I can't zoom out anymore. Damn. Okay, so yeah, that went very, very far. Didn't stop until 66 seconds later. So what two things really kind of affect the driving distance on the moon? So light pink was on Earth with air, on Earth with no air resistance is purple. Green on the moon with air resistance, this bright pink here on the moon. Yep, can't. Haven't figured out a way to zoom out of this. Or, well, yeah, so this guy was the no air resistance and the same gravity of the moon. All right, so they're definitely going to go farther on the moon than on Earth because of the fact that there is very little to air resistance slowing the velocity down in the x direction, and the fact that there is less gravity pulling the ball downward, right? So if you dropped anything, you drop your pen or pencil right now in front of you, direction it falls down is or the direction it's going to move is down. So if you, let's say we round it up to make it easy numbers. If I threw a ball straight up at 40 meters per second, gravity is negative 10 meters per second squared going downward. That means basically it's going to lose 10 meters per second worth of speed as it tries to move upward. So if I launched it at 40, 1 second later it's going to lose 10, so it should be at 30. The next second should be at 20. At 3 seconds it should be 10, and then at 4 seconds it should have lost all of its speed in the vertical direction. And then it's basically the next second later, it should be down at negative 10, and then negative 20, and then negative 40 back until it like hits your hand. But if you were to do the same thing on the moon, it would take 6 times the amount of time for that to occur, because gravity is 6 times less. So the fact that gravity is not pulling the ball down nearly at such a great rate gives it a tremendous amount of more height and hang time in air. And if there's no air resistance or very little air resistance, there's really nothing impeding the ball's motion in the x direction as well. Okay, so that, guys, should help us answer all of our questions. All right, obviously you're going to want to edit them around a little bit. Make sure you have everything complete and answered, and then you guys will be able to submit that.